Hi everyone. In this lecture, I will talk about proof by division into cases. This is the last method of proof that we see in the second chapter. The idea of proof by division into cases is very simple. First of all, it is easy to show that this argument is valid. You can either prove it by constructing a truth table, or you can use the resolution rule of inference that we saw in the beginning of this chapter twice and show that this argument is true. Let's first take a look at this argument and see what it claims. It says if there are two cases, either C1 or C2, and each case implies Q, C1 implies Q and C2 implies Q, therefore Q must be true in all cases. So it's a very obvious rule. There's an extension of this argument that we can see in this part of the slide. It says if C1 is true or C2 is true or C3 all the way to Cn, which means if there are n different possibilities or n different cases, and each case implies Q, C1 implies Q, C2 implies Q, all the way to the last one, which is Cn implies Q. Therefore, Q must be true for all the possibilities, which means Q is true. So based on the argument that we saw in the previous slide, we can define a new method of proof, which we call it proof by division into cases or proof by cases. If you want to prove a universalist statement using a proof by cases method, and the universalist statement is for every x p of x, and let's assume that the domain of x is D, you need to first break the domain D into different subsets or subdomains. Let's assume that D is equal to D1 union D2 union D3 all the way to Dn. And then after breaking the domain into different classes, you need to give a different proof for each class, which means that you need to prove the same universalist statement for D1. You need to prove the same universalist statement when the domain is D2, all the way to the last class. You need to show that the universalist statement is true when the domain is Dn. If you show that all of these classes make p of x true, then you can claim that no matter which class x belongs to, p of x must be true. Let's look at a simple example of proof by cases or proof by division into cases. Let's assume that you are asked to prove that for every integer x squared minus x is an even integer. So how can we prove this? If you want to use the method of proof by cases, you need to first assume that there are two cases, x is either odd or x is or even, right? The first case is when x is even, and the second case is when x is odd. As you see, case 1, x is even, case 2, x is odd. So this is how we divide the domain, which is the set of all integers, into two classes, class of even numbers and class of odd numbers. Now you have to provide a proof for the statement, for the claim in each case. So for the case that x is even, for case 1, you need to provide a separate proof for the claim, and for case 2, where x is odd, you need to provide another proof for the claim. And if you do this for both the cases, you'll be done. So let's first take a look at case 1. When x is even, you can write x equal to 2 times k for some integer k based on the definition of even numbers. Then you can replace x by 2k in this expression, in this algebraic expression, and after plugging in x, you will have this expression that can be simplified to 4k squared minus 2k, and you can factor out the 2 and get 2 times 2k squared minus k. 2k squared minus k is an integer because integers are closed under addition, multiplication, and subtraction. So we prove that x squared minus x is equal to 2 times an integer, and therefore x squared minus x is even based on the definition of even numbers. In the second case, when x is odd, x is equal to 2 times k plus 1 for some integer x, and therefore you need to replace x this time by 2k plus 1 in this expression. So you have 2k plus 1 squared minus 2k plus 1, which is equal to 4k squared plus 2k. And again, you can factor out the 2 and say it's equal to 2 times 2k squared plus k. And since 2k squared plus k is an integer, therefore x squared minus x is written as 2 times an integer, which means that it is even based on the definition of even numbers. Now let's take a look at another example. This example is about absolute value of x. We know that absolute value of x is equal to x if x is non-negative, and absolute value of x is equal to negative x if x is negative. So let's look at this theorem about absolute value of x. It says, prove that for every real number x, absolute value of x is greater than or equal to both x and negative x. The question is, how can we prove this? And we can use the fact that for any real number x, absolute value of x is non-negative. It can be implied by the definition of the absolute value itself. So let's prove that absolute value of x is greater than or equal to both x and negative x. How can we prove this? We need to consider two different cases. A real number can be negative or it can be non-negative, which means greater than or equal to 0. In the first case, we consider the negative case. In the second case, we consider the non-negative case. If we prove the claim for both cases, then we are done proving that absolute value of x is greater than or equal to both x and negative x. Let's take a look at the first case. When x is negative, we can put the two inequalities. Absolute value of x is greater than or equal to x, the fact that we agreed on, and x is negative together in order and get this chain of inequalities. Absolute value of x is greater than or equal to 0, and 0 is greater than x. So based on the transitivity of inequalities, we can simply say, therefore, absolute value of x is greater than or equal to x, right? But the question was prove that not only absolute value of x is greater than or equal to x, but also it is greater than or equal to negative x. So here is another statement for proving that absolute value of x is greater than negative x. We say that since x is negative, by the definition of absolute value, it is equal to absolute value of x is equal to negative x. So since absolute value of x is equal to negative x, it is also greater than or equal to negative x, which means that we have proven the other inequality for the first case too. Now let's take a look at the second case. In the second case, I should also prove both inequalities, and if I do that, then for both cases I have proven both inequalities and I'll be done proving this theorem. In the second case, when x is greater than or equal to 0, since negative x is less than or equal to 0, why? Because you can multiply this inequality by a negative one and then the direction of inequality changes. Therefore, negative x is less than or equal to 0. We can put this inequality together with the fact that absolute value of x is greater than or equal to 0 and get the following chain of inequalities. Absolute value of x is greater than 0 and it is greater than or equal to negative x. Therefore, negative x is less than or equal to absolute value of x by the transitivity of inequalities. Now, I need to prove that absolute value of x is greater than or equal to x for the second case. Since x is greater than or equal to 0 by definition of absolute value, we can say that absolute value of x is equal to x. Since it is equal, it is also greater than or equal. Therefore, we can say that we have proven both inequalities for both cases and we are done proving the theorem.